Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is July 4th, 2017. The title of this lecture is AC RLC Series Electrical Circuit Analysis. In this lecture, you will learn how to calculate the variables involved in an alternating current resistor-inductor-capacitor or RLC series AC electrical circuit. The typical AC electrical circuit consists of control systems which regulate both current and voltage using individually oscillating and alternating voltage and current sine waves as depicted below in the following drawing. Now we will solve an AC RLC series electrical circuit for the following variables below. Taking what we know from the circuit, we can answer some of these variables. From that point, we must go down and conduct a circuit analysis for the given circuit. So we know that the total RMS root mean square voltage is 85 volts for the circuit of AC voltage. The circuit frequency is 92 Hertz. The total resistance involved either from the power station or a contained grid is a resistance of 150 ohms. The total inductance 850 millihenries, which means if we divide that by 1,000, we have 0.85 henries of inductance, a total capacitance of 75 microfarads, which means if we divide that into 1 million, 75 over 1 million, 1 millionth is micro, whereas 1,000th is milli. So when we do so, we get a whole number of farads, 7.5 to the 1, 2, 3, 4, negative 5 power farads. The inductive reactance is the first value we must calculate. This is equal to 2 pi times the circuit frequency, which will equal the angular frequency of the circuit times the inductance in henries. When we do so, 491.3 ohms inductive reactance. Capacitive reactance is equal to 1 over 2 pi times the circuit frequency, which is the angular frequency of the circuit, except this time times the capacitance in farads. We must take the inverse of this quantity or its reciprocal. So when we do so, we have 23.1 ohms of capacitive reactance. The total reactance is the difference between the inductive reactance and the capacitive reactance. When we do so, 468.2 ohms total reactance. I will get to why there's inductive here in a second, as opposed to capacitive. Next is the impedance of this given AC series RLC circuit, denoted by Z sub S, as opposed to the impedance of a parallel RLC AC circuit. That would be equal to this formula here, the resistance squared times the total reactance squared, added together as a quantity with the square root of. When we do so, we calculate an impedance for this AC RLC circuit of 491.6 ohms. The total current in the circuit would be equal to the total RMS effective voltage, E sub T, divided into the impedance of the given circuit. When we do so, we calculate 0.17 amps RMS effective current, AC. Voltage drop across the resistor would be equal to the total current times its resistance in ohms, or 25.5 volts RMS voltage. The voltage at the inductor is equal to the total current times the inductive reactance, X sub L. When we do so, 83.5 volts. The voltage at the capacitor is equal to the total current, RMS, times the capacitive reactance, so 3.93 volts. Note that the current will always be constant in a series circuit, whereas voltage is not. So if we need to know the current at the resistor, inductor, or capacitor for the circuit, it's all equal to the total current of 0.17 amps RMS, effective current. Power factor in a series AC RLC circuit is the ratio between the voltage drop across the resistor divided into the total RMS voltage of the circuit. So when we take these values in a ratio, 25.5 volt RMS voltage drop at the circuit's resistor divided into 85 volts RMS total AC voltage for the circuit, we calculate a power factor of 0.3. The apparent power is equal to the RMS voltage total times the RMS current total. When we do so, we have 14.45 volt amps. Apparent power is not the same as true power. It is a loading in the form of volt amps. Where the actual true power occurs is when the volt amps are multiplied times the power factor. And when we do so, we calculate a total power, actually a true power output for this given circuit of 4.34 watts. Next, the phase angle, as we will go back to the first diagram. We have a phase shift in degrees, or phase angle, between the voltage and the current sine waves. And obviously the voltage here is lagging the current. The current is coming sooner over the function of time. So if we go back to calculating the phase angle of this given circuit, that would be equal to the inverse cosine of the power factor, or the inverse cosine of 0.3, so 72.54 degrees phase angle for the circuit. And then lastly, the relationship between the voltage and the current for the circuit. The current will lag the voltage by a phase angle of 72.54 degrees, because in an AC series RLC circuit, the current will lag the voltage when the voltage at the inductor is greater than the voltage at the capacitor. We know that current is constant in a series electrical circuit, so we have to focus on what the voltage is, the difference between the voltage at the inductor and the capacitor. Because the voltage is greater at the inductor L compared to the capacitor C, this circuit is inductive in nature, as proven by the voltage drop at the inductor. We got to look for E sub L is 83.5 volts RMS, whereas the voltage at the capacitor is 3.93 volts. So that means this given circuit is inductive in nature, as opposed to being capacitive in nature. And because the voltage is greater at the inductor compared to the capacitor, the current will lag the voltage by a phase angle of 72.54 0.54 degrees. So this means that the voltage is dominant and coming sooner than the current. And in an electromotive application, the voltage dominates the RPM of the motor and the current dominates the torque of the motor. So if this was an application where the RPM was more critical, this given circuit at its given setting would be sufficient to satisfy that torque curve on the motor. Many times when circuit analysis of AC power takes place, equipment is used to calculate all of these variables. However, there may be points where the phase angle may have to be manually calculated, and to do so mathematically on algebraic terms, this is how you would do it. The more you do these problems, the more repetition and consistency will allow you to know that when the when the voltage is greater at the inductor compared to the capacitor in a series AC RLC circuit, the current will lag or come before the voltage. And then there's a certain phase angle which can be used for diagnostics purposes and also to know the power factor. For example, if this was an AC motor and the amperes were constant, it would be sufficient to run a constant torque output electric motor, AC electric motor, for which the RPM would be fluctuated while maintaining a relatively tight torque curve. So a series would be more acceptable. However, in the real world, voltage staying constant in a parallel circuit, or RPM having a little more constant speed, where torque factors are more controllable through amperes, is more practical. But this is somewhat or very important when it comes to the diagnostics end, especially on the maintenance level, diagnosis and quantification of a system, then matched to the given engineering specifications. The analysis become a lot more easier to work with. And of course, you may have a tablet or a device, digital watt meter, digital VOA, that you can put these all into real-time charts, but it does help to gain mastery on the circuit analysis. So when it comes to AC, RLC, electrical circuits, you're going to want to know all of these variables so you have control over what is going on with a given circuit. Thank you for watching this video and have a great day.